All right. So talking about here about the first one, Joey.
So first, just wants us to find the eigenvalues in basis.
And how do you find eigenvalues again?
Well, I guess we don't have a triangular matrix here.
We don't. We do have kind of the next best thing. We do have a block triangular matrix.
Yeah.
You could do that. And you do observe real fast that 4 is an eigenvalue. And then this piece down there. So recall, if you have a block triangular matrix, or now B doesn't have to be a square matrix, but A and C both have to be square matrices. Whenever you take the spectrum, you take the eigenvalues of A and the eigenvalues of C, and you smash them together, union them, you do get this. So that's a nice little fast little trick you can do to speed this up a little bit. So really, you're just looking at a 2 by 2 case. And if I want to figure out the eigenvalues for a 2 by 2 case, I can also very quickly write its corresponding characteristic polynomial. We'll say PC here, where we'll have t squared and then minus the trace, and then plus the determinant. So you would have 6, and then minus 2, 4. Factor, and you see that your eigenvalues are going to be 4, 4, and 1. Now, make sure if you're writing in terms of the spectrum, to write in terms of a multiset. Repetition is important in a multiset. That's what the spectrum is. If I just said you had eigenvalues 1 and 4, you might think I'm just talking about a 2 by 2. But I'm really talking about a 3 by 3 here. Okay. Now, next thing is find a basis for the eigenspace. Well, to find a basis, really what that is synonymous of saying, hey, find eigenvectors. So lambda equals 1, and then lambda equals 4. Okay, do you remember how to go about that? Okay, take it back to the definition if you need to.
Yeah.
And what you're solving is you're finding the non-trivial solutions for this. Because remember, v can't be 0. In other words, take the eigenvalue off the diagonal. Something like that. And this is awesome because look right here, 3 and a bunch of zeros. So when you have a row that has a non-zero entry in it, man, rejoice, because what you're going to do is pivot down as fast as you can and just knock those entries out. And then look at this. It's the same row, just been scaled. How sweet it is. And there is your singular matrix. Put into parametric vector form, and you see that x1 needs to be 0, whereas x3 is going to be the free parameter. It is what it is. So your eigenvector is going to correspond then to, pull out the x3, that right there. All right. Let's take a look at the next one. So the other one we had lambda equals 4, and that's going to work out the same way. So we're going to have things 4 up the diagonal. And get that. And I can already see singular matrix, row 4 zeros. If you take the first or the second, add to the third, it's going to zero things out. Do a quick row swap. Put into parametric vector form. Maybe first solve for x1 makes it a little bit easier. But there it is. So you're going to take this and get your other vectors. These are your free variables. Take it, yank it, pull it apart, separate it, recalibrate, and then here are the x's, plus, and you just found basis for your eigenspace. Good. Okay, let me pause there and we'll see if that's making sense.
I think for the like finding the eigenvalues of the block matrix, like so you just, I'm not sure if I fully understand like.
Okay. Now you can always just go back to the run of the mill where you're just taking the characters polynomial of the 3 by 3. That would work. This is just a little fast little shortcut. And I'm not sure, not all classes teach that in this particular class. But if you were to take t off the diagonal, this is something I usually show my students just so it helps them out a little bit more. But if you were to do a deflation argument where you first off do the cofactor expansion, you would take this, you'd multiply this, and then you multiply by this 2 by 2. Then you'd pick up 0 and then 0. So everything else is going to zero out. The only thing that survives is that piece. And if I was to take this, even make it a little bit more challenging, let's say 4, 1, 0, 3, 2, 5, 0, or 1, 2, 0, 0, and then 3, then 4, then 0, 0, 1, and 6. You can do a very similar argument here, where maybe instead of expanding across the first, expand across the last row. And as you go across it, you're going to pick up 0. Then you're going to pick up 0. Then this is the first term where it doesn't pick up 0. But if you were to look at it in terms of a block matrix, that's the bottom block. And you do have to go through this. You cross this out. So as you cross it out, what's the point of having those values? It doesn't contribute at all to the whole grand scheme of things. Then you would look at this 3 by 3. See if I can shade that. It's a little hard to see there. And then you do another deflation argument. You would do the cofactor expansion, and then look, there's a bunch of row zeros right there. You expand across it, and then that last column didn't really matter anyways. And what really matters is that 2 by 2. So it's just a nice little trick you can do.
Yeah.
Try it later on. Convince yourself of it. It has to be a square matrix for these to work. You could technically have something that looks like this. And that trick would still work. You just got to have a block of zeros. Now, block doesn't mean it has to be square, it's just some kind of block, so it resembles a diagonal system. This is what you need to look for, Joey, whenever you have like 4x4 and 5x5, because they're more than likely not going to throw you a 4x4 or 5x5 if there wasn't some kind of trick, some kind of structure they wanted you to observe. Because otherwise it's way too complicated.
Yeah.
Okay. Now, here's the question. What's the algebraic multiplicity of the eigenvalue of 1? How many times did it appear as a root? It just occurred once. When you look at the spectrum, it just occurred once. That's why it's really important to write it down in terms of a multiset. When we look at the algebraic multiplicity, how many times did 4 appear as a root? Okay. Now, here's the geometric multiplicity. Remember what that one was called? What that referred to? Eigenspace.
Oh yeah.
How many
Oh yeah.
basis vectors do we calculate? Eigenvectors, in other words, for lambda equals 1.
1,
How many basis vectors do we calculate for lambda equals 4?
2,
A matrix is going to be diagonalizable, provided that the algebraic multiplicity equals the geometric multiplicity for every single eigenvalue out there. So for any eigenvalue that you find within the spectrum, if you can conclude that's not just some of the times or just a little bit here, a little bit there, but for all the times, if these two things are the same, A is diagonalizable. We'll say bull like that. That means I can put this into a similarity transformation where it is entirely possible to state that. The question is, what's my P matrix here? I come back to the second part of the problem. How do I figure this thing out? And the answer is, look at the eigenvectors. What you're going to do is slot in your eigenvectors. Doesn't matter how you do it. You can put the third one here if you wanted to. It doesn't matter. But what's going to happen here is whenever you go through multiplication, you're going to observe that you would have eigenvalue 1, the third one, however you calibrate it, and then the second one. So these entries are based upon what's happening here with the columns. And this diagonal matrix, everything else is 0. Okay. Good. Feeling pretty good about it?
Yeah.
Awesome. All right. We'll give you a moment to see if you have another question about this problem.
Yes, so algebraic multiplicity and the geometric multiplicity. So for it to be
Yeah, diagonalizable. Say it 3 times fast and then backwards.
they have to be the same.
The algebraic multiplicity always has to equal geometric multiplicity, otherwise it's not.
Okay.
Now, you can get the kind of the next best thing where it's not really a diagonal matrix. It might be something like this. Where this is something called your Jordan canonical form, but you're going to pick up a 1 up here and you can't get rid of it. So it's the next best thing. But if you had diagonal matrix, that's awesome if you can get that because it really makes calculations easier.
If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.